Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. My name is Sonia Lalo and I've been walking you through the physics class. In this lesson on the fundamentals of electronics, we'll be considering the conduction in solids. We'll look at semiconductors. We'll talk about the types of semiconductors. Then we'll consider the PN joints, diode, then diode characteristic curve, and then center tapped full wave rectifier, then the bipolar joint transistor, and conclusively integrated circuits. Alright, let's begin. When we're talking about electronics, what comes to mind? What always comes to mind include our televisions, our radio sets, and other things as such that we use in our houses. These are electronic devices, and all these electronic devices do contain a lot of circuits, a lot of connections which are required for them to function. In the midst of all these connections, we see many of these things are made of solid materials. So that makes us need to study the relationship between conduction in solid material, electric conductions in solid materials. We definitely are sure that there are two major types of materials. We have those ones that we know as the conductors and insulators. We discussed them prior to this time. We have materials that we describe as conductors. These are materials that allow the free flow of electricity through them. And we have the ones we describe as insulators. These are the ones that do not allow the flow of electricity through them. But this, in between the midst of the conductors and the insulators, there is a group, a special group, which is regarded as the semiconductors. Semiconductors. So what are semiconductors? Semiconductors allow the flow of, allow partial flow of current through them. Before we go so much into semiconductors, let's take a break now. And in a short while, some questions will be displayed on your screen to test the knowledge of what has been taught so far in this particular lesson. Please answer these questions. We want to know what you understand so far. Thank you. Welcome back. So earlier we talked about conduction in solids, and I mentioned that we have two major different types of materials, the conductors and the insulators. Then I also introduced a new class, a different class of materials which actually fall in between the conductors and the insulators, and they are known as the semiconductors. So how do semiconductors operate? What is the reason? Why do they exhibit these unique characteristics? Alright, the reason is simple. For the flow of electric current from one particular place to another, for a flow of electric current from one place to another that is through medium, there are certain properties that there's certain requirements that should be met. There must be free electrons. These electrons are described as valence electrons. There must be free valence electrons in the outermost shell of the atom of that particular element. So if there are no free valence electrons in the outermost shell of the element, then there will be nothing to carry the information, that is the electricity which is being released. There will be nothing to carry it, which is being imputed or being released into the system. There will be nothing to carry it to the other side. So this the pattern in which electricity flows through solids, it's like messengers. The electrons are like the messengers. They carry the message and they take it to different destinations. So most of our solids, most of our conductors have one free outermost electron, two free outermost electrons. So these are the major ones that we do have. But in the case of the the ones that do not conduct, those are the non-conducting substances, also known as the insulators. They have their outermost their outermost shells either completely occupied or occupied in such a way that the electrons are choked up. The electrons are stacked. They cannot move freely. So because they cannot move freely, they find it difficult to transmit electricity from one point to the other. Well, in the semiconductors, what do we have? The semiconductors are made up of elements which are of the group 4 in the periodic table. They're made up of elements, mostly group 4 in the periodic table. And these elements are usually described as metalloids. They have 4 outermost electrons. So in a way, they can receive just as much as they can give electrons. They can receive just as much as they can give electrons. They don't give more, they don't receive less, just equal. So because of this nature, they tend to give only when certain conditions is being met. As a result of this, we do have them becoming selective when electricity is being passed through them. So on your screen, in a few seconds, you see 3 different blocks to show the description of the conductors, the insulators, and the semiconductors. In insulators, a large energy gap is present. A large energy gap is present. That is the amount of energy required to transmit electricity. The gap that is there is much. So because of that, the electricity is not able to pass through. In conductors, you see that even the energy gap is like a dash, and the blocks, that is the conducting blocks, they interlock, they cross into one another. So that is the normal metals. The energy blocks, the conduction block band, the conduction band enter into one another. They interlock. While in the semiconductors, there is a small gap which require a relatively small amount of electricity to be overcome. So if that particular amount of electricity is passed through it, then electricity might actually flow through the system. Let's look at the types of semiconductors. The types of semiconductors. We can classify semiconductors into the pure and impure types. That is, based on their makeup. Based on their makeup, we can classify them into pure and impure types. So how do we group them into pure and impure types? The pure types mean they contain just one metal, probably a metal like carbon, silicon, or germanium. All these metals, or rather metalloids, they do have 4 electrons in the outermost shell. They are metalloids. So they on their own suits. They are suits for the purpose of the semiconductors. They can function as semiconductors on their own. While the impure substances, impure ones, are not metalloids. Rather, they are made up of group 3s and group 5s. Group 3s and group 5s. Well, in the group 3s, we see elements like aluminium and the rest of them. Now, we interact them with group 5s, where we see elements like sulfur and the rest of them. Now, what happens is this. The aluminium or boron and the rest of them do kind of react. They do react with the phosphorus and the group 7s, in such a way that they blend together to form a new substance. So when electricity is about to pass through this new substance, the new substance allows electricity to flow based on it begins to ionize each part, because they are like, you have phosphorus, or you have aluminium on one side, and you have a phosphorus on the other side. Aluminium is 3 plus, phosphorus is 3 minus. So the electrons from here come here trying to, they're trying to lose the electron, trying to gain the electrons back, and that's how the electricity is being passed. So there is a limited amount of there's a very limited amount of currents that would be able to pass through, because the electrons are not so free as that. So the system will become balanced at a particular point in time. That's how we describe, that's why we consider this one, because it does not contain one singular element, unlike carbon, where we have carbon blocks, of course. A carbon block, can say both of them are plus, and can say both of them are minus, because anyone can be labeled plus, anyone can be labeled minus. This one can lose to this one, and then this one will lose back to it the same quantity. That's in pure substances, but this one, where they are impure, this one will lose to this, and the best it can do is to return what it has lost to it. So that's how these semiconductors do operate. Alright, in the impure substances, we have the group that we describe as the donor impurities. The donor impurities. This group contains elements like phosphorus, like arsenic, and the rest of them, all the group 5s. The group 5s in the periodic table. Now, these elements have 5 electrons in the outermost shell. So they actually are the ones that do accept the electrons that are coming from the other ones. Of course, they'll find it more difficult to let go of 5 electrons. So this end of the system are usually described as the N or the negative part. So they form the N or the negative part of the semiconductors. Also, we have the acceptors impurity. Acceptor impurities, just the exact opposite of this, contains elements like aluminium, germanium, indium, and the other them. They are mostly group 3 elements. Group 3 elements. And of course, since they lose electrons, they tend to come out to be the positive side. So they are described as the P, that's the positive side of the semiconductors. So in the semiconductors, we have the positive side, we have the negative side. The group 3s occupy the space of the positive side, because they are the ones that lose electrons, and of course when you lose electron, you become positively charged, and these ones are the ones that receive the electrons to become negatively charged. So when the electricity is passed through, they are called the donor, because it's they that have enough electrons that can afford to move around to bring about the passage of electricity in the system. So it is electrons will move from here and take the charges over there to ensure that the electricity is passed through. Electricity flows through the system. Okay, let's consider the PN joint diode. In the PN joint diode, just as we have described semiconductors, that we have 2 types of them, the pure ones and the impure ones. Considering the impure ones now, because those are the ones that can possibly have PN joints, we have a description, a kind of block like this. While these ones are positively charged, these ones are negatively charged. Of course, they are in the same they are in the same system. So the gap exists. Now when electricity is being passed, is attempted to be passed through the system, this gap kind of like splits up into two. It splits up into two, and this part of it becomes negatively charged. It becomes negatively charged because it is closer to a positive, and this other side of it becomes positively charged. It becomes positively charged because it's closer to the negative, and as such, electricity is going to pass through it, but very, very, very limited and in a controlled manner. That's what happens in the PN joint. So this layer between them, where the positive and negative do develop, is known as the depletion layer. What is a diode? A diode is an electronic device that allows the flow of electricity only in certain direction. It controls the direction in which we want the electricity to flow. It helps us to rectify or correct electrical systems. So in the midst of all of this, how do diodes find their place? Good question. Peradventure, you have an alternating current system. In the alternating current, we know that current flow, the profile is something like this. The alternating current system can be transmitted or converted into a direct current system by the use of a diode. So what will happen? The diode would allow the flow of electricity from one side to another without allowing the flow in the other direction, and we will have something like that coming out of this. The down parts of it would not occur. So that is what the diode would do in a condition like this. So we use a diode to serve as a rectifier. Well, we'll still be looking deeper into how we actually get to the level of full rectification. That's when we talk about full center tapped full wave rectifiers. But now our diode can be forward bias and it can be backward bias. Like I said, the diode will only allow the flow of electricity in one direction. So it can allow the electricity to go forward, or it can allow the electricity to come only backward. So depending on how we want to do it. Like this profile that we have up here is a forward bias profile. A backward bias profile for this same flow would be something like this. The other part of the wave, only half of the wave is allowed to flow. So when it says it is forward bias, it means it only allows the electricity to flow forward. When we say it is backward bias, it only allows the electricity to go backward. It chooses one of them and allows one, prevents the other. About the diode characteristics curve. The diode characteristic curve. The diode characteristics curve is a graphical description of how the diode works. On your screen now, you'll be seeing a particular curve which shows that of a particular diode, a PN diode. Of course, we can have a PN system, we can have an NP system. It shows that of a PN diode. Now, this, of course, allows selected amount of electricity to flow. That is selected amount of voltage to flow. So, for a forward bias system, when we have something like so, in a forward bias system, of course, the electricity flows like that. And when the electricity flows like that. When it flows, it enters in and it comes out. So we want the electricity to flow through. This is the forward bias system. In the reverse bias, we have something a bit different. Instead of the electricity flowing in line with the same with our diode, it is flowing in opposition to the diode. Now, if it is a reverse biased diode, it will allow this electricity to enter and to exit. But if it is not, it will simply block it off. It will cut it off. If it is a forward biased diode, it will allow this particular one to enter and to exit. If it is not, it will simply cut it off. So this is our forward biased system. And this is for our reverse bias systems. So minus plus, plus minus. So that's how the systems are designed. When we come to the rectifiers now, rectifiers are used to control, they're used to fix issues, especially issues in systems. Peradventure, you are having an electric current. How do we charge our phone batteries? How do we charge our devices? We have very many devices which are supposed to be AC, DC, that is, they are supposed to operate using direct current. But when we want to charge them, we use alternating current. The light entering our houses from PHCN or from our generators are alternating current based. That's why when on your generator you notice that it's kind of fluctuates consistently. Well, the light from our batteries, our phone batteries, our touchlight batteries, they are all direct current. So how do we kind of like create a bridge, a connection between these two? That's where the rectifiers come to play. I showed us the other time how a diode tries to rectify alternating current so as to produce direct current. Of course, the original wave profile of the alternating currents is something like this. And so we have what we call the half wave rectifier. The half wave rectifier. In the half wave rectifier, we have one diode connected to a system. Probably we have a resistor, probably not, but let's just place a resistor there. This is an half wave rectifier design, and the products would be something like this. That would be the output. The other half of the entire system can also be created by introducing to get this other half, which is something like this. We can introduce another diode to the system. Probably we have something like this. Well, this is our diode. Of course, this is our resistor. And this is our cell. So what would come, in fact, let me not place it before, let me place it after. What this would output would be something like this. Most likely it would still look like this, but when the two diodes are installed together on the same platform, what it will give out would be something not exactly like this. Anyways, it would, instead of it being down, it will bring it up. It will produce its own also up. So in the full rectifier system, what happens? You have two different diodes. We have two different diodes connected across the system. So we have something like and our output becomes this. So no electricity is lost. All the electricity input is now being converted, and everything is now going to flow in the proper direction. Of course, the electricity will go in and exit, go in and exit. So it will simply allow all the electricity to flow in the forward bias. All the electricity have now been controlled. The backward bias is now being converted to a forward bias. The downward flow is now being converted to an upward flow, thereby creating a kind of direct current flow in the system. So our direct currents are known to have something like this across them, and that's what we'll be experiencing sort of here. Although yes, there are still some fluctuations, but to a great extent the fluctuations do not go into the negatives anymore. So that is how our nothing will come down again in alternating current. Because it's going, the way it's going to come out is supposed to be half. That's the backward bias. It's supposed to be half, but the diode would flip it. Since it is a forward bias diode I'm connecting, it will flip it, so it will appear to be up. The truth is all these things are like they are watching the time. It's not all. This diagram is voltage time. Voltage time. So at this particular time, in this particular diode, this is the first diode that it was noticed, and that one will produce this up one. Now, at a particular time that this diode is supposed to now go down, electricity will be entering inside this one. So instead of this one going down, this one will not allow electricity to pass through at that particular time. But this one would now start allowing electricity to pass. So instead of it going down, it will go up again and fall. By the time this one is falling back, the time that this one is not receiving electricity would have been elapsed. So this one will not conduct electricity again. This one will take over. And that's how it works. So that's how the center tapped full wave rectifier. Talk about the bipolar joint transistors. Well, transistors are also used as rectifiers. They are also used to rectify current, that is the flow of current in this particular system. But in this particular case, when we talk about the bipolar joint transistor, it means that it contains two different poles inside it, and in our transistors we have three legs. So how is it possible for it to contain two different poles? Well, basically to make our transistors we need semiconductors. We need semiconductors because it is selective, and our transistors have three legs which are known as the emitter, the base, and the controller. The emitter, the base, and the controller. So we usually see they come with E, B, and C. All right, come with E, B, C, E, B, and C. So our bipolar joint transistor also has the EBC structure. The only thing is it is dependent on what we want to use the transistor to do. Now, where the EBC can be a PNP system or an NPN system. It can be a PNP system or an NPN system. In the PNP system, of course, we have the positive side, the negative in between, and the positive, of course, and they are arranged based on this arrangement. So in the PNP, we have our emitter is positive, the base is negative, and the controller is positive. While in the NPN, the emitter is negative, the base is positive, and the controller is positive. In a few seconds, some diagrams will be displayed on your screen to show you exactly what the circuit looks like. Okay. From the diagram you can see on your screen, you can see how the circuit is connected. The center part is always earthed, is always connected to an earth, while each of the other sides are connected to electric cells. That's cells where current can be passed in. Now, this particular process is known as the biasing of the system. Is known as the biasing of the BJT, that is the bipolar joint transistor. Also, you also see another description of you see the description of each of the components, how to come about with a common base, how to come about with common emitter, how to also connect for common collectors. The reason why we have to learn all these things is so that we can understand the calculations that might be involved when we are connecting these devices to when we're connecting this to any of our devices which we are developing. Also, let's go over the PNP and the NPN systems one more time. The PNP system, our emitter, of course, is the first, that's positive, then the base comes afterwards, which is negative, then the controller comes, which is positive. While in the NPN system, the emitter, of course, comes first again as negative this time around, but the base comes positive and the controller comes again negative. So, still on the joint connections, we see all right, let's take this particular one to use to create a kind of awareness in us. We want to take note of all the connections, all the flow of electric current in the system. Now, in this particular system, we can tell that current, definitely, there's the current of the controller will come in and to flow downward. Of course, current is also being initiated at the base, and also currents would flow here based on the direction given. That's current of the current of the emitter, so it will go out of the emitter. So that's how the current flows through the emitter's distance. So if we look at this particular system based on the Kirchhoff's law, we talked about Kirchhoff's law before this particular class. Based on the Kirchhoff's law, we can always conclude that IE, that is the electric current flowing through this particular system, is going to be equal to, of course, we know that there is current being passed into the base. So it's going to be equal to the sum of the current from the controller and the current from the base. So with this, with this, we can go ahead and make some of our calculations. Now, our transistor is used as a current amplifier. Is used as a current amplifier in most cases. That's why in churches we have a particular board called our mixer. Sometimes we call them amps. Yeah, it contains a couple of circuits which mixes a lot of things together and amplifies the voice of the person speaking into the microphone. And then we have a loud volume sound coming out of the megaphones and other speakers. So this is one of the secrets involved in this production. It amplifies anything that goes in. A little wave will go in and it would amplify it. So we have two types of gains, that is two types of amplification that occur in the system. We have two types of gain that can be observed in the system. These are the common base gain and the common emitter gain. The common base gain and the common emitter gain. Why don't we have the common control gain? Of course, it's at the control point that we do experience whatever thing that is coming out of the speaker. It's the control that goes out to our speakers. So, how do we calculate the common base gain? The common base gain is calculated as common base gain alpha. The common base gain, known as alpha, can be calculated as the current through the the control divided by the current through the emitter. The current through the control divided by the current through the emitter. While the common emitter gain, recognized as beta, is calculated by current through the control divided by current through the base. Current through the control divided by current through the emitter, and current through the control divided by current through the base. So this actually show us a couple of things that can occur. These are actually the ways we can calculate the amount of amplification that is experienced in the system. So also, it is good to note that when this occurs, there is also an amplification of voltage. Yes, there is the amplification of voltage. Since we know that voltage equals to IR. So basically, to calculate our voltage, it depends on whichever kind of system you're using, whether it is a base or is a common base system or the common emitter system. But generally, whichever one it is, we can always calculate our voltage amplification, voltage amplification as V out divided by V in. Voltage out divided by voltage in. To get that, you can just calculate whichever one that you are, based on whichever one you are using, and the value of your I would remain the same value for your voltage amplification. Alright. Let's discuss integrated circuits. As lovely as technology has reached today, it is possible for you to actually have a whole computer system right in your palm. In fact, I'm looking forward to the time where we would need to carry nothing and would have our computers with us. So this is being made possible based on several different inventions and innovations that has come to play over the years. Back at as of the 18th century, sorry, how do they calculate 20th century? Back as of the 20th century, our computers always had to be a full TV which had a lot of circuits. In fact, our full TV back then in the 1990s, in the 1980s, in the 1970s were connected with a lot of circuits. And today we have the LED systems, the LCD systems, flat surround TVs. You can have a TV as small as your hand, just like your smartphones. They serve also as the same function as your TV. In those days, you don't see such things come to be. Why? Because we had a lot of components that needed to be connected together to create those particular devices. Today, these components have been simplified you can have up to 1 million transistors connected together inside a very tiny device, which even works faster than the normal 1 million transmitters and transistors that we used to have back in those days. And this device is what is known as the integrated circuits. So what do we call integrated circuits? Just like the words say, they contain several circuits ranging from thousands to millions, even billions of circuits inside one component, and they are integrated, means they are gathered together, incorporated. They have become a singular device. So it is the knowledge of transistors and capacitors. You can have several capacitors and transistors, inductors, resistors, all put together to form just one singular integrated circuit. Your normal computer's processor is an integrated circuit that has over 1 billion systems, 1 billion different circuits inside it. Back in those days, when the computer system was newly invented, it would take a whole house to build a computer. Today, everybody walks around with a computer called a mobile phone, a smartphone. You can do virtually everything you can do on your computer systems on them. And this is because of the creation of integrated circuits. So we have two types of integrated circuits. We have the ones we call the linear or the analog integrated circuits, which contains transistors and oscillators. They are used for doing jobs of transistors and oscillators. And we also have the digital integrated circuits, which are the most common these days. They are used for switching, system switching, circuit switching. So that's one of the reasons why we can have up to millions and billions of circuits in one particular IC. Of course, integrated circuits can be shortened into IC. Our digital integrated circuits can also be further split into two: transistor logic, and CMOS. The CMOS, which is a complementary metal oxide semiconductor logic. Now, the transistor logic are faster. They are faster than the CMOS. They're faster than the CMOS, but they require stable and very large amount of electrical current voltage for their operation. Meanwhile, the CMOS are slower, but they can work with low voltage. So you see many people talk about different processors. Then you see CMOS processors, you see TTL processors. All these things are made up of a lot of circuits that have been put together to ensure that these things are very functional. Let's talk about the operational amplifier. It's an integrated circuit, and it is the most versatile. It's one of the most versatile integrated circuits. So the operational amplifier is also known as op-amp. It is the most versatile integrated circuit, and it comes in its operations are in two different ways. It can be the non-inverting, and it can also be the inverting. For the non-inverting op-amp, we have an expression for the gain, the voltage gain. The expression for the voltage gain is given as VO over V1 equals to 1 plus RF over R. For the non-inverting op-amp, we have this expression that holds for it. That's to calculate the amplification. The amplification, that's R out, that's output voltage over input voltage, equals to 1 plus the resistance of the feedback divided by the resistance of the system, the internal resistance of the system. So this is the rectifier, and what's it called again? This is our transistor inside the integrated circuit, and this is the connection which we have. We have the input voltage and the output voltage. This is grounded and this is grounded. So the amount of voltage that will exit it would be higher than the amount of voltage that would enter into the system. But in the inverting op amp, it's a little difference. There's a little tweak in the inverting op amp. We don't have our resistance here. So in our inverting op amp, we have a little difference. Instead of our resistors being connected to each other kind of in series connection, is going to now pass through a lot more complex system and resulting into a parallel connection of the resistors. And of course, instead of the voltage measuring directly from earth to the positive side, it now measures from earth to the back of the resistor, which is connected in series to the connected towards the negative part of the transistor. So at the end of the day, we'll come up with a formula which is very different. It is an inverting. So it is a negative amplification. So it's like it is reducing the amount of voltage that comes out. And obviously you can see our VI would likely be greater than our VO. So our VO divided by VI also would be now minus RF divided by R1. So let's take a pause at this particular point in time, because other things we can come across things that we can look into are things that are quite advanced beyond the ordinary O-level physics. So in this lesson we'll consider the fundamentals of electronics. That's the introduction into electronics. We looked at the solid conduction in solids. Also looked at how solids do conduct electricity. We talked about conductors and insulators. We looked at semiconductors as well. Then we talked about the different types of semiconductors which you have, and then we went to the PN joint diodes. After we discussed the PN joint diodes, well, we were talking about the semiconductors made up of two impure substances. We looked at the diode characteristic curve, and we showed an example of what it looks like and how it is used. We also talked about the center tapped full wave rectifier after talking about the half wave rectifier, and we showed how it converts alternating current into direct current. Then we went to discuss the bipolar joint transistors. The bipolar joint transistors having three different forms of it: the common base, the common emitter, and the common controller. But we disregard the common controller because they have no use to us when it comes to voltage amplification. And we discussed voltage amplification as the voltage output divided by the voltage imputed. We also went straight to discuss integrated circuits. We mentioned what integrated circuits are, applications in our real and where we can find them in being applied, and also we talked about the inverting and non-inverting operational amp, being the operational amplifier being one of the most versatile integrated circuits. After spoken about all these things, some questions will be displayed on your screen in a few seconds. You're required to answer them, and if there is any part of the questions which proves challenging, you can go back to view the video, to look at the video, to watch the video, so you can get better clarity on the subject matter. Thank you.